Hi, so welcome for the next speech. I will talk about real-time video analytics with InfoSphere Streams, OpenCV and R. And the first thing I should mention, I've created a live demo, so I will show most of it live, but I've also created some slides, and I have, to enable you to recap the live demo, I've created slides about the live demo also, you can download afterwards. I haven't created this one alone. Wilfried Hoge was another colleague who created the live demo with me, so for the recognition, it's not my own live demo or just single my own, it's also Wilfried's. So my name is Stephan Reimann, maybe a few words. I'm working with large-scale data warehouse and streaming analytics already for several years, and I work for IBM. The first thing is why I wanted to do something with video. So one of the motivations was everybody is talking about unstructured data, and whenever you talk about unstructured data, 90% of the people or more are talking about text. And I think that's not all. So there's more than just text. So why not using image data? Why not using audio data? Why not using even moving image data, so video? And as a use case, we thought, what could be an interesting use case? And I think one of the most interesting data sources right now in big data is sensor data created by machines. So it's about making machines smarter. So the idea was, okay, let's do something in the context of sensor data, of machine data, but let's do it with video to show, hey, there's something beyond just pure sensor data. And let's do it in real time, of course. And so what kind of machine could be of interest to use for real-time data? So that when I went to a vacation to Berlin, I saw this picture, which was for creating a new metro tunnel. And afterwards, I went to another place, and I saw kind of a tunnel drilled as used for instance, for metros. And the thing is, you have two conflicting goals there. The first one, you want to have it running as fast as possible to earn as much money as you can. The faster you are done with one tunnel, you can go to the next one. But if it's going too fast, the problem is it will cost you a lot of money to repair it. But what's the right speed? And that's basically a problem with a lot of industrial machines. So it's just one example for industrial machines. The tunnel drill is like a small fabric or a small plant. And so the idea was, if you could use data science to say what's the optimum speed, why not doing it? Just to give you some context. And so we said, okay, it would be of interest to analyze what's on the conveyor belt here. So what's going over there? Are there metallic parts? Is it what kind of stone or whatever? And combine this maybe with sensor data like the weight, like the structured data, like the speed of the conveyor belt or whatever. And if you detect any problem, you can stop the tunnel drill immediately to prevent damage. So you would have the use of this. And, okay, we did not have a tunnel drill, so we said, let's create it from Lego. Basically, this is the Lego equipment we have created. It's about 60 centimeters long, so this time I didn't travel with it. It's a bit unhandy. But it's basically a picture generator or a video generator to experiment, and this is if you use it with the analytics stuff on the side. So I usually use the iPhone to just get the pictures. And so the idea was, okay, let's do streaming analytics right on this. And I will just go into the live demo. Okay. I should switch. Okay. And the first thing, now you have seen the first ingredient, which is the data. Our tunnel drill in this case is the data, and I'm just analyzing a single camera since I'm just doing it on my laptop, and I wanted to show a functional demo. The second thing you need is some kind of software to do the analytics. And in our case, we have decided to use a combination of commercial software, which is InfoSphere Streams, a streaming analytics product based on an IBM research project. It was, I think, even partially created here in Zurich, or parts of it, and some open source components such as OpenCV or R. And the first... Okay. Everything fine. This is my streaming application. So it's like, where do I have it? It's a concept that most streaming analytics solutions use. The analytics, the application is kind of a graph, and the data is flowing through. And before I show you what's happening or how this graph looks, I will show you the result. So the first thing is I have this large data stream, okay, it's just a single camera, and I want to get pictures out of it. I want to get information out of it, but I'm not interested in the conveyor belt. I want to see what's on it. So I want to make a foreground and background separation. Since the conveyor belt itself is just useless information, I know how it looks. And what I'm doing is I use machine learning. In this case, it's this codebook operator. So you see, the first thing I do is I do crop the picture, so I remove things I definitely don't need, since this is the original picture. Then I do some kind of data cleansing, so I use a smooth operator, which is just removing some small details. So of course I will also lose small details, but I will also lose some noise of the image. And then I've used the codebook operator, which is a standard algorithm from the OpenCV toolkit that can learn a moving background. So you can learn a waterfall or whatever, and in my case I just said, please learn the first 20 seconds. It's just important, in the first 20 seconds you should have nothing on the conveyor belt. Since the idea is quite simple, I have a data stream, I don't know what I want to get out of this data stream. Since I can't explain it, there could be anything on this conveyor belt. Since I can't explain what I'm looking for, I say, okay, let's build a mathematical model of what I'm not looking for, so kind of outlier analysis, and this is what I'm doing here. And this is what the codebook operator does. It learns the conveyor belt, so the things I'm not interested in, and now I do real-time scoring, and of course I have to remove some noise afterwards, since you see all white points are classified as foreground, all black ones are classified as background. And the connecting component algorithm is just another algorithm for reducing noise. And this apply to is just you use these masks here and apply to the original image, so you have all pixels blacked out that are background. And how is it implemented? It's quite simple. Well, usually InfoSphere Streams is not the right tool to visualize this. I just created it for the demo so you can see something, and it's quite nice to see. This is the application that does exactly this. I first import the picture, and then I have one operator that does crop it. So I have to say what's the top left and the bottom right corner. It's nothing special, and that's a standard algorithm. And then I split it. I have here the original picture, which will later on go to this apply, since I need the original picture. And on the lower part, I do all this stuff like smoothing, and this is also a standard algorithm with some parameters, in this case, the number of iterations, and the learn background operator. So this is the codebook operator. As said, it's a standard algorithm, and the only thing I configured is how long should it take to learn. And this I go through the steps, and all these export stuff is just for visualization, so you don't need half of these operators. And this is how it works. In 4 or 5 simple steps, I was able to, separate the background from the foreground to get an idea of what of the interesting things in the picture. And now I can start to move on with some more sophisticated stuff. For instance, I could say I want to analyze, or I want to, let's say, calculate some measurements on the things I see, things like the area, some kind of color saturation, or a histogram. I don't have it. So whenever something goes over this conveyor belt, now you see there's also kind of a bit of latency here. Then it calculates, for instance, the area in pixels. It tells me the absolute values for red, green, and blue. And on the lower part, I visualized the histogram. So these are like features. If you're interested in image analytics, I've also provided some links in the presentation. There are basically 2 concepts how you handle this image recognition or image classification. One thing is you calculate features from the picture. And color is a very simple feature. It could be shape, it could be anything. I have a classification in a feature map to give you an idea in the presentation. I think there are about 50 common features you could calculate, and then you use a combination of those features with machine learning to say this is maybe a person, this is maybe a part of this type. The other this is the classical approach. The newer approach is neuronal networks. But I think it's with neuronal networks you need a lot of compute power, so I'm not sure how to get this really in a low latency context. That's something that's outside of my area of expertise. And what I could do now with these numbers, and this is what we have done, we have just said, okay, why not using R to just do some simple predictions on this? So I've used the R operator, and it's basically operating using two scripts, one to build the model and one to score it. And I can show you, should be somewhere here, R analytics. So I have a build model script. It's not really sophisticated mathematics. We wanted to have a stable model just to show a few things. So it's a bit of data preparation, so classification stuff and so on. And then it's basically a decision tree, since this was quite stable on a small amount of learning examples. And then I have a second script that does just the scoring. So whenever a picture goes through, or when the application is started, the model gets built, and with every picture gets scored against the built model, and the result, you can see if I start the application. So it should start now. Okay. Okay, now nothing is on the conveyor belt, but yes, there's something, and now it's classified as being a red object. Red is usually is quite good in detection with this one. It's just based on, I think, on the absolute values for red, green, and blue, since it was the simplest thing to create a model. Of course, you could do any kind of complex model on this. You can see my finger, and yeah. This is what you started with some, let's say, with this video analytics stuff. It's just showing the possibilities. And if you look at the data itself, those images are not vector graphics, they are pixel graphics in this case. And we could even have a look at them. I'll zoom in. It's just like a big matrix. So it's a lot of zeros and some color values. We have it. Okay. Show data. Okay. Here. Let's check. So maybe I can show you one picture. Okay. So you see, this is basically it's a list of integer values I could show you, but it's every image is quite big, and probably on a laptop visualizing this big matrix is not the best idea in an Eclipse environment. But it's okay. It's just a picture with a different number of channels, and each channel has a list with the individual values for each pixel. It goes in a certain order in the IPL image format. Maybe some closing words about InfoSphere Streams. You have seen I have extended it. Usually you have a large number of toolkits already included, like the time series toolkit. You have adapters for TCP, UDP, data mining. But if you miss something, and this is what we have done here, since the OpenCV toolkit was nothing that was included, or video analytics, you can use your own code and integrate it here, and then you have the operators, and you can just then later on use it with drag and drop to really simplify application development. So it's a good example of how you can use a toolkit approach that is extensible with your own code. I think it's fine. And if you look why it scales, since I always say you can do all these streaming analytics with your iPhone or any kind of smartphone. Take the camera, and if it detects any kind of face, it draws a box around it. It's like streaming analytics. But the idea here was to make it scalable. And if you look, this is the logical architecture of my applications. It's the data source, it's the background-foreground separator. This is just for visualization. This was calculating the area and the histogram, and this is the R part. But if you look at how it looks on the system level, on the system process level, this is how it scales. It distributes all those processes across a cluster. Okay, this cluster in my case is just my laptop, but you could use thousands or hundreds of nodes or tens of nodes, whatever you need. And this is how you scale these applications and how streaming analytics gets scalable. I think this is quite common also in other kind of software. Yeah, but to give you an idea, so there's a big step between iPhone and scalable streaming analytics. Yeah. And if you are interested in knowing more about it, there is a nice webcast on YouTube, and the link is provided in the presentation that explains, first of all, how image analytics is done with all this feature stuff, how you can try to classify images. So this is some theoretical background from an IBM research education series, which is quite interesting, I think. If you're interested to play around by your own, then I have provided here the most important links. So there's a free quick start edition for InfoSphere Streams if you want to try the same software. There's also other streaming software on the market, of course. There is a developer community where you can get tutorials, labs, and so on. And also those toolkits like the OpenCV toolkit is on the GitHub community. And of course, OpenCV and R are just the regular open source things you already know. Some words, I think I've already said a bit about InfoSphere Streams. It's just a recap. So the idea is InfoSphere Streams has been built to analyze, to make streaming analytics scalable, to be able to analyze any kind of data, whether it's image, text, or sensor data, or structured data, with any kind of analytics, whether it is machine learning or just a simple filter, at the speed the data is created with ultra-low latency. And ultra-low latency means if you have, it can go down to a few microseconds, so it's even below milliseconds. And some final remarks about, I've shown you a nice, hopefully you have enjoyed this example of video analytics and this tunnel drill. But streaming analytics is not just the future, it's already present. So even in Europe, what we use it for at IBM, for instance, is in our semiconductor production and manufacturing. So we analyze all those test data from the wafers to let's say, directly optimize the production process in real time. So the idea is if you detect a part that is no longer of any value and you can abort this process, you will avoid machine hours, person hours, and very valuable material. And those manufacturing processes are running hours or days. So you can really save a lot of money and use the Streams software to analyze all this tester data or the sensor data from the testers. But also there are clients using it in mobile phone networks, for instance, analyzing those metadata, especially if you have a high amount of prepaid customers that are highly likely to move on if they are not happy with your service. And if they have a dropped call, they get quite immediately a 50 short messages package or whatever, kind of a compensation to keep them happy. But it's also used to optimize the traffic in Stockholm or whatever. So there are quite a lot of use cases where streaming analytics is already a reality. But the reason why I wanted to show this in the industrial use cases, since this is really one of the trending topics, using sensor data to optimize manufacturing in real time. And at the end, if you're looking for your streaming analytics use case, I said it's not about technology. I think technology is ready for prime time, whether you're using InfoSphere Streams, Spark, or whatever. They are all a bit different, but of course there are different approaches. But there's only one question you should be able to answer. What can you do if you have information in real time, and what benefit can you achieve? So the first thing is, that's important to mention, what can you do? And usually the result of streaming analytics is kind of an action or an alert. So it's not I have a report that's constantly refreshing. I want to say this part goes out of the manufacturing process. I want to say I want to stop this machine. Since I sometimes have to smile, people are discussing about latency, and the next question is, how do you visualize it? I said, what's your reaction time? It's not possible to react in microseconds, at least I can't. The second part of the question is, you must have this information in real time, but data usually is not the problem. And the third thing is, what is the benefit? So can you save material? Can you save person hours? Can you reduce risk? Can you make new markets? Maybe if you say, okay, if I provide the service in real time or kind of alerting, maybe I have a new customer service. And this is basically all the questions where I would always recommend to start if you are considering streaming analytics or real-time analytics. Questions? Any questions? Nobody?
I was wondering about the crop operator that we're using, because most pictures that you get are, in German, they're calling fallende Linien, so they are distorted in some way. So why didn't you use a real distortion operator that clears the distortion? Like here you have this falling line, these horizontal lines.
First of all, I wanted to have always the same image size, since it's easier to for the visualization part. Since when the merge operator expects me, the one I will show you, that has put all those 5 close to each other, expect me to have every picture I want to merge in the same size. So I needed a fixed size. It's just the way this operator works. Otherwise, it would crash. So I needed a defined size of the picture, and so I said, okay, I just used the crop operator. But of course, it was just a sample that you can do more sophisticated stuff with it.
Any other questions?
Is there a Watson node operator thing?
In InfoSphere Streams? Not yet, but you can create any kind of algorithm. So, but what the things we have usually, or things I often use, are everything from machine learning for data mining. So we have integration with SPSS, with R, with the classic tools where you can apply all those machine learning algorithms. And basically it's about scoring. So you have a model.
Maybe my question is more: is there predefined model libraries? Because, for example, when I have Watson, then what I want is I want to show something to Watson, and then Watson says, yes, I recognize it. This is a house, or something like that. And the question is, what you've shown here is pretty basic, okay? Calculate the number of pixels that are read on the picture. And the question is there something that goes beyond that already, or are we still in the first basic steps?
In terms of application logic, not, since InfoSphere Streams, what I used here was basically built as kind of a middleware component to make streaming a little scalable. It's not, let's say, a ready-to-go business application. If you look, for instance, at our Bluemix cloud, there are Watson APIs where you can do image classification and so on that are more on the application part, but it's a different level, and you're not on a software level, you're on the API culture. And there you have, of course,
I covered that now. You can
Okay.
So maybe is there last question? Otherwise, I just take over. Okay, so